Hi, welcome everyone. Thank you for coming to our webinar here today. My name is Patrick Kenny. I am Senior Director of Marketing Communications for Invest Ottawa and Area X.O, operated by Invest Ottawa. For those of you who are not aware, Area X.O is the R&D complex in Canada's capital that enables and accelerates the safe and secure development, testing, and application of next-generation technologies. Area X.O has unique smart city infrastructure and physical assets and leverages one of the most advanced communications infrastructures in the world. All of these capabilities allow Area X.O to offer limitless testing capabilities for breakthrough innovations in mobility, autonomy, and connectivity. Until recently, Area X.O was limited to the physical world, but this past winter, Area X.O launched a simulation discovery portal powered by ANSYS. The simulation portal and program promotes simulation and its ability to reduce time, cost, effort, and risk by getting breakthrough innovations to market faster. Innovators now have a new option to consider. Which brings us to today's webinar. It is my pleasure to introduce Area X.O simulation engineers Barry Stout and Hossein Sami to share their expertise on simulation as a tool, provide examples, and answer your questions. And before we begin, here are a couple housekeeping items. Please enter your questions or comments through the chat panel, which is located to the far right-hand side of your console. To submit, you can either click the icon or press enter on your keyboard. We will have a specific Q&A period following the presentations. We also have two poll questions we will be asking. The first one we'll put up now, asking which sector you represent. The poll will close in 5 minutes. The second question, which aspect of simulation you are most interested in, will appear towards the end of the webinar. Poll results are going to be tabulated and then circulated as a post-event email. Well, it's time to get going, and it's now my pleasure to ask Barry Stout to walk us through today's presentation. Barry?
Thank you, Patrick. Hello, everybody. My name is Barry Stout, and I'm presenting our webinar on simulation. I'm just going to put up my screen. Perfect. So, for the agenda today, we'll start with the introduction to about the Area X.O simulation team, just in brief about me and my coworker, Sami. Then we'll dive into what is simulation. Thereafter, we'll break down the different methods of simulation, finite element, and digital image engineering. Why is simulation important? Then how does it reduce time, cost, and effort? And how does it reduce risk in product development? Thereafter, we have the simulation portal to show who wants to sign up. Then Sami will come in with doing some demonstrations, and thereafter we have some questions. Sorry, give me a second. There we go. So, about my colleague, Hossein Sami. He is one of the simulation engineers here. He specializes in robotics and aerospace. He has a master's degree in the field of robotics. He's been working here since November 2022, so which is about a little more than 7 months. And his work experience includes aerospace manufacturing, drone flight testing, and rocketry and experimental aircraft. About me, my name is Dr. Barry Stout, the presenter of today. My specialty is in propulsion and power. So I earned my doctorate in plasma propulsion at York University. I worked in the Area X.O since November 2022, so about 7 months. And my previous experience was including defense in the space sector, which include aerothermodynamics research, radar technology development, and next generation communications. I also worked in energy systems, which worked on thermoelectrics as well as plasma torches. So let's get into it. What is simulation? Simulation is an artificial representation of the operations of a physical model. They take the model to represent different characteristics of the system. So, for example, you can take a car, aircraft, wood on the table. If that's how it be in terms of physics, you could be economic models of a country. The simulation or simulator manipulates the model with the constraints. In our case, in most cases, it will be in physics-based. On the right, this is a model and simulation of AirX.0 test track using enhanced AV Accelerate or AVX. We'll get more into that into our demonstrations. So besides that, the real-time simulator, we have two other type of simulations that we want to explain. One is finite element analysis, and the other is digital mission engineering. So what is finite element analysis? Finite element analysis, or FEA, is a numerical technique to solve physics models. I'll provide a high-level explanation as this area is quite complex. It starts by a digital model. It could be any model from CAD, so it could be ANSYS Space Claim, it could be AutoCAD 360, Fusion 360, it could be SolidWorks, and so forth. And it's paired with a numerical solver. So this numerical solver will be, in this case, ANSYS. So the numerical solver solves several inputs, such as boundary conditions, initial conditions, and environmental conditions. So anything that you put constraints into the model. Then the two are then computed, and then the computer will solve the equations and output the data. Finite element analysis solves for mechanical structures, thermal analysis, electronics, and optical. You're asking yourself, so why is it called finite element analysis? So finite element really means that we're taking a model, let's say this patch antenna, and then we create a mesh of it, break it down to different elements, and each of the elements has been solved into a large matrix. It could be thousands or tens of thousands of rows and columns. Therefore, this is called finite element analysis. After the finite element analysis software is finished to run, the results are illustrated for the engineers to analyze the behavior of the system. So the illustration could be two-dimensional, like this electromagnetic radiation results from this patch antenna, or from the thermal analysis of this server, which is a three-dimensional. Next, we're going to go into digital mission engineering, or the simulation that does systems of systems. In digital mission engineering, we start by having an engineer think about a scenario anywhere around the world. Thereafter, he put in his asset, where it could be a drone, it could be a satellite, a car, aircraft, or anything like that. But for our purpose, we'll put in the drone. So this asset will perform duties like the intelligence gathering, and will spy over or interact with an aircraft, a boat, a car, but it doesn't have to be adversarial. It could be a piece of land or a city. And that asset also will also have some allies in this case. It could be a SATCOM to communicate its data from, and a ground station. Now, this is just a unique scenario. It could be any scenario that the digital mission engineer wants, as so long as it comes down, is breaking down within the real world aspects. Moving on. So we have our scenario. So then the simulation engineer will put in the inputs. So the inputs could be time of day, it could be route, the sensor types, and so forth. And the output will be data. So that data will come to the engineer, and the engineer will analyze it to make sure it makes sense, and make other than make common sense, also physics and scientific sense. And here, one digital engineering software is Systems Toolkit. Here's an example of the Arctic scenario. So for those who want to know more about it, there will be a demonstration after this. So just giving you a taste of it. So why is simulation important? First, it stimulates innovations. Engineers are not bounded by the physical world when building their products. They can make it in any shape, size, and any other characteristics that model it. Second, it enables visualization of the products to the engineers and non-engineers. The designer can provide a preview of how the product interacts with the real world, such as stakeholders can understand the ramifications. Simulation reduces time, cost, and effort in the product development as well as mitigating associate risk. Those 2 points, which is the topic of this webinar, will be answered in the subsequent slides. Finally, it presents a feasibility report to potential investors to make sure that your product will work and will have impact into any sort of market. So how does it reduce time, cost, and effort? Once engineers develop their digital prototype, they can adjust the dimensions and conditions of the model and simulation. If an engineer creates a physical prototype, and it has not worked as designed, they must go back and rebuild it from scratch. Instead, simulators can adjust the dimensions of the model and test them in a scenario. This reduces the cost of building expensive prototypes, the effort in redesign, and the time of manufacturing. Another aspect is putting the model under various environmental conditions that would be otherwise too expensive to test in real life. Having the right environmental condition for testing is tough, very tough. Let's say the engineer wants to test a sensor in a major blizzard in downtown Ottawa. They can just look at the weather number to see when it will be, but what if we're here right now on June 7th, in the middle of summer? Should he wait until January to get the blizzard to test his product? No, it doesn't make any sense. Thus, the simulators can simulate the blizzard conditions at a touch of a button, and then they get the result within a short period of time. This aspect reduces the time needed to put the product onto the market, as well as the cost to set up the test in the ideal condition. Thirdly, optimize the design to get the maximum performance, minimum cost, or other attributes. Making the best product on the resource available is the key to keeping an SME afloat. Simulation enables design optimization to get the maximum performance with a minimum cost. Engineers can adjust other parameters to get the ideal product they want. This aspect reduces the effort in product optimization via standard hand calculations. So instead of going through a hand calculations and going through iterations, which will take time, you can have a simulator that actually goes through the optimization for you. So then it reduces time, effort, and cost. So how do we reduce risks in product development? So how does it? Let's explain through some examples. Autonomous vehicle sensor in a high traffic area. SMEs need to train their artificial intelligence machine learning algorithm to have the autonomous vehicles to be fully autonomous. Putting an AV on a physical street can be expensive and dangerous if not careful. However, having a simulator like AVX paired with a car simulator, let's say Carla or a car maker, allows engineers to test their algorithm in a digital twin, let it be trained, and don't have to worry about putting people in any actual danger. Wireless device behavior in the area of interest. Wireless communication is everywhere, and people are using their mobile device constantly, actively or passively. Here's the problem. What if you have a drone that requires constant connectivity in that area, and a signal should not be dropped below a certain threshold, let's say 5 decibels, for example. With SDK, we can simulate the communication map and see how well the wireless communication will perform before sending out an actual drone for testing. Assessing the camera's performance. So a lot of companies want to have the best cameras just for their automated vehicles or remote sensing. So it could be for your drones, satellites, and so forth. They will set up various scenarios with the camera to see if it has the correct visibility. Therefore, simulating this camera system with SPIOS or SDK can assure engineers that their systems function correctly before building it. Thermal integrity of a prototype in a hazardous condition. Let's say that you have a brand new device, onboard a car, drone, satellite. However, the engineers do not know how well it can perform under conditions like high temperature fluctuations. So let's say that you have a satellite that orbiting, and you have a sensor on there, and it fluctuates between normally negative 15 degrees Celsius to 80 degrees Celsius. So with SI wave and ice pack, engineers can test the prototype under harsh temperature conditions and observe the signal integrity to reassure themselves that the system will not suffer performance degradation or be destroyed during operation. Lastly, aerospace vehicles performance in various mission areas. So you have an SME that wants to launch a new remote piloted aerial system to monitor the Pacific Ocean, which is kind of huge, but let's say a small part of a Pacific Ocean. It is connected via satellite in the geosynchronous belt or low Earth orbit, but we could say geosynchronous belt just as long as there's connectivity. The engineers want to make sure that the vehicle is performing its duties during operations and that the ground operators are assured that they'll have constant connectivity regardless of latency. So whether it be like 10 milliseconds to 750 milliseconds, as long as they have reliable connectivity. SDK enables this mission to be digitalized and analyzed by engineers and subject matter experts. This seemingly helps reduce the risk of the product not functioning in a high-stress situation where you could lose a $5 million drone just because you didn't test it out in different scenarios. So there you have it. This is where we have how what simulation is used for and how we reduce risk, time, effort, and cost. So join our simulation community for free. You'll learn about the benefits of simulation. So you'll see an interactive Area X.O's assets in a virtual environment. You can access curated content. You can access answers and math for computing software. You can also be if you sign up, you'll be informed more about future information sessions. Sign up is free to unlock the resources, and the content is only available at our Area X.O simulation community. The link right here, I'll put on my later pointer, it's areaxo.com/simulation. Very simple. Sign up, and you will have a access to our platform. Thank you for your attention.
Thank you, Dr. Stout, for walking us through that presentation. It was enlightening and I think provided a lot of answers to people who have posed questions in the past. What we're now going to do is actually present some practical examples of simulation through some demonstrations. We're also then following that going to enter into a Q&A period. So if you have any questions about any of the material that has been presented up until this point or through the demonstrations that are going to be shown, please add your comments and questions in the comments section, and we'll build a list of questions to ask during the Q&A. Okay, please enjoy these demonstrations.
So hello everyone, I'm Sammy, and I'm going to be giving you a short demo of what we can do with ANSYS AVX. ANSYS AVX is our autonomous driving and sensor simulator. So we're able to simulate multiple sensors in a digital environment. What we have done at AreaX.O is digitized the entire site into the ANSYS platform. Right over here, you can kind of see what this looks like. The model includes our entire site with all of its different zones, as well as the infrastructure. Zooming in, we're able to see a lot of the finer details that are included in this model. We have our main building where most of our staff is located, as well as all the traffic signs, nature, and other infrastructure that has been set up, as well as the farms. This digital twin also includes the infrastructure embedded into our smart city zone. This includes a multitude of sensors, which have optical cameras, roadside units. Right over here, we also have some thermal cameras, as well as LiDAR cameras. These sensors, as well as multiple more, are embedded into our site where they're physically located to mimic the real-world scenarios in the simulation before we actually go to conduct our tests. As we were mentioning, the site is extensive, including all the road markings and other small features, as well as our railway crossing. So that can be also observed here. And we're able to simulate the arms moving down and up as would be normal in our typical use case. In addition to this, the model has also been allows for easy adjustment of different weather conditions, which includes fog as well as snow, which is one of my personal favorites. Here we'll kind of give you a teaser of what that looks like. So yeah, it allows you to test in different weather and lighting conditions. So at night, day, you mention it, without actually having to wait for those scenarios in real life. Now that we have a decent idea of the environment that we're simulating in, we can move on to defining the sensors on our vehicles. So the different sensors that we are able to simulate are shown here. We're able to simulate cameras, LiDARs, including flashing and rotating, as well as radars. For a quick demo, I'm only going to be presenting the data from the camera, because the LiDAR and radar require additional interpretation. When we go to define our camera, we're able to define all of its physical properties as shown here, and all of this results, it allows for the ANSYS simulation platform to compute the physics behind what is going on. So once we have our sensor defined for whatever we chose, we're able to define our test vehicle and define where the camera or other sensor is located on the car. For this demo, we'll just do a demo car, just the Lexus, and the camera is going to be located right at the front of the car. So, yeah, not the most realistic, but this will let us have a good view, a good and clear view of what's going on in the environment. So once we have our car defined as well as the sensors on the vehicle, we are able to move on to choosing a car simulator. Currently, we support a lot of different softwares. We're able to run simulations using IPG CarMaker, Carla, and also using Weebots. So this is a look at the program we're going to be using to co-simulate with ANSYS AVX called Weebots. We have another copy of the AreaXO site imported into this platform, but as you can already tell, it is nowhere close to as accurate as our ANSYS model. This model includes basic buildings and some of the roads, although they're not all exactly accurate. So in order to do a demo, what we're going to do is we're going to simulate a car driving on this site and compare it, or not compare it, but connect it with ANSYS AVX in order to get a practical demo. We'll start right here, looking at our main building. So let's do that. There you go. Yep, so it's going to show up to tell the connector what's going on. Oops. Sorry about that. And let me just get this aligned so that we're ready for when the simulator is running. Okay. So while we're waiting for the simulator to set up, I'll kind of give you a little more detail into what's going on here. So with Weebots, you can define your vehicle, including its suspension, wheel model, the powertrain on it, and other features to define, the vehicle dynamics of the car. We already defined the sensors that are attached to this vehicle in the AVX platform. So once we have all of that defined, the Weebot simulation tells us how the vehicle is going to move, and we're able to control it, telling the vehicle where to go, and also program autonomous driving algorithms. These scripts can be input directly into Weebots to tell the vehicle how to respond when it detects certain objects, and these scripts can be written in Python or C. I'd have to give it a little longer here while we're waiting for AVX to load up. But once it does, what you'll be able to see is that the exact position of the vehicle is going to show us the view of what the digital twin looks like in the AVX environment. And oh, there it is. So yeah, here you're able to see we're able to transfer everything right over. I'm gonna move the car a bit, and you can see the digital twin also moves pretty much right the same way. Okay, so we're pretty much going to drive along the track to kind of show you that, yeah, everything works out. Oops. Yeah, right now it's a little difficult to drive using the keyboard, but you can see it works pretty well. So yeah, so VBOTS is only here to define the position and the orientation of the vehicle, but what we really care about and want to focus on is the AVX, right? So let me move this out of the way so we can actually look at that. Yeah, it's right here. Yeah. So now you can see we're able to control our vehicle and drive it as we please. And this is where the different autonomous driving algorithms come in. You're able to program so that the vehicle can either turn, speed up, slow down as you wish based on what it sees in this environment. For this example, we've included just an optical camera, but as was shown, we are also able to include radar as well as flashing and rotating LiDAR sensors. All of this data is available to the autonomous driving algorithm to determine what is the best course of action. You can see as we pull up to the intersection, all of the different sensors embedded in this environment are all visible in this model even. We're able to stop at the intersection and yeah, that kind of demonstrates what we're able to do with this model. Tutorial, I'm going to be going over STK and what that allows us to do with the ANSYS. So STK is a systems toolkit, and it lets us simulate air and space missions. It's a digital mission engineering tool. So this allows us to model drones, aircraft, satellites, etc. Anything moving large distances over large time. So the first thing I want to give kind of an overview is the SDK has a global view of the entire planet, right? You're no longer limited to just Area X.0, but you can simulate your missions and flights over anywhere on the Earth. For the demo, though, we will focus on a mission that is conducted at our site, Area X.0, and we'll be doing some scans of a farm. So here you can see there's two views. We have the 3D view as well as the 2D view of the Earth, right? So we'll zoom in here and you'll kind of see the area that we have defined as our site. So yeah, right around here, we have the Area XO site, and I'll zoom in the 2D view as well, just to so we're all on the same page. Yeah. Yeah, you can kind of see same area on both. That's okay. So first thing we did is kind of define the different targeted areas, right? So as I'm sure you might know, that Area XO has a lot of experimental farms in our area. Monitoring these farms would be very labor and time intensive, so the use of drones to scan the fields regularly to provide a detailed update of crop growth and status is very helpful. So the mission we're going to simulate is a drone leaving our main office around here and going to scan one of these fields. So the first thing we wanted to find is some ground station, right? So right over here, I've added a ground station of just our mobile command center. So it's we're assuming our Lexus, and we can add the details about the antennas, so the frequency it's operating at, as well as the radiated power. This allows SDK to model the physics of what's going on. There are further details that can be used to model additional gains, filters, you name it. But so yeah, so right now we have defined a ground station with an antenna that our drone is going to try to communicate to. Then we can start defining our drone. So over here, you'll kind of see the setup of what's going on. So in SDK, we're able to choose various different drones. You can see we're able to capture airliners, business jets, fighters, helicopters, and so forth. These models are not limited to small drone applications and can be extended to large-scale practical aircraft or even satellites. So for this demo, we're using a quadcopter. So this is going to be a rotorcraft, and here we can kind of see the different models. So we're able to define the performance of our drone. So the max altitude, different dynamic rates that it's able to maneuver at, as well as safe and transition airspeeds for the aircraft. We also define the rotors size as well as blades, and this allows SDK to compute the aerodynamic performance of our vehicle. Yeah, so if we fill out all the corresponding information, we end up with a very accurate model of a drone that reflects its actual performance. Right here, SDK is kind of calculating all the stuff, so we'll give it a second to get its work done. Okay, awesome. Moving on, so once we've defined our aircraft, we then proceed to defining the mission. So as we said, for this scenario, we're going to take off very close to our ground station, right? That's our ground vehicle that we set up antennas from, and then the pilot exits and deploys this drone. The drone is first going to take off from that takeoff pad. Then it's going to transition into forward flight. And over here we can see transition to forward flight. Yep. And then it's going to proceed to, we'll choose farm 1, right? That's the biggest one, probably take the most power to scan. So yeah, once it reaches this area, we're able to define the altitude as well as the density with which it should scan this field. So we've set a 400 feet separation between passes, and it's going to try to scan this field, maintaining this distance of separation. Okay, apply this. And at the end of the mission, we're going to return to the takeoff location, transition to hover, and then land on the pad, right? So if we apply this mission, right, note that there's no need to define the times you need or what the power setting is necessary to fly the drone. All of this is computed by SDK. What's necessary is to define where you want to go after where, and if there is a position you need to be at a specific time, you can also define that to make the drone wait there until it reaches a specific time. So once we've defined our mission, you click OK, and SDK will compute the mission trajectory to satisfy those characteristics. So here you can kind of see SDK has computed a path for us, and this is what it looks like. The drone takes off, goes to the farm, scans, and once it's done scanning the entire field, returns to the site. So here you can kind of also visualize this trajectory in 3D, right? And this shows you clearly where the drone starts. Kind of see here, it takes off to a minimum safe altitude and then proceeds to a flight altitude to conduct the scan, maintains that altitude during the scan, and after the scan is done, descends back to the safe altitude before landing. So we can also visualize this in a video. So let's see. Going to Click OK. Zoom back in. And yeah. There we go. Zoom 2. So this kind of lets you see the drone. Right? So you can simulate and see what exactly the drone is doing for the entire flight. So as we saw earlier, the drone takes off vertically from the launch pad. Then it starts on the trajectory. We are going to speed it up a little bit since it takes a while. But you can see the drone, conducts this trajectory to scan over the entire field, maintaining that distance of separation that we specified, right? And then at the end of this, it goes back and lands, right? So that concludes the mission, and we were able to verify that, okay, yeah, it does indeed scan the entire area, and there's no obstructions or anything that we need to worry about. So we'll stop that here for the simulation. Yeah, so that's a flight planning portion of using SDK. Now, beyond just planning for the flight, we still need to determine whether this trajectory is feasible for the drone. In order to do this, we can go into the report and graph manager. So here we're able to get a lot of information about the flight. A lot of these contexts are very specific to space application, but for our sample here, what we want to know is the flight profile and the power consumption over this flight. This will allow us to determine whether the flight is feasible or not. So let's go to a real quick scan. Yeah, so here you can see the SDK reports the power required at each second throughout the trajectory. So yeah, it gives you a step size every second, the power required in order to keep flying. Horsepower is not the most convenient, so we're going to switch it to watts. And yep, you can see the data. So what we're able to do then, let's take slightly larger time steps so we can work with this faster. What we're able to do then is take this data and plot it to determine to visualize the data and determine whether it meets our necessary mission. I was kind of checking this out earlier, so you'll be able to see that it's set up. But yeah, so here you can see that we have the power needed for each time, and I'm calculating the energy consumed based on that. We have a battery, 3-cell, 10 milliamp hour, 10 amp hour battery, and we're able to verify that indeed the flight takes about this much energy. The flight is concluded right around here. We're looking at about 20 minutes. And the flight does not need more energy than the battery can provide. So this allows you to verify whether your trajectories are feasible. Okay, awesome. Now, the other great thing about SDK is you're able to modify the trajectories with relative ease. So let me do that. Let's say, for example, for the max separation distance, instead of 400 feet, we wanted something a little more dense, so around 200. We're able to set this option, apply, and SDK will recalculate the trajectory in order to meet the new mission requirements. Once we hit apply, and give SDK a minute to compute. Yeah, so you're able to see how these paths are much more densely packed. This allows for much lower degree of distance of separation and a more dense scan to get data in very close locations. But such dense trajectory, it might not be necessary. That's okay. Yeah. So that kind of gives you a flavor of what might be able to do. And you can also modify which farm you want to go to, and SDK will again pre-compute everything that you need. So the other thing that is very important when we're doing these simulations is to ensure we maintain a line of communication with our drone at all times. So we've added a receiver onto the drone, specified here, and we were able to define a lot of these special parameters that let you define the physics of what's going on and get more accurate model. With this, we're able to define, we can plot the transmitter coverage, and this lets us visualize how the sensitivity, the connection strength over the area. Right, so we've defined a grid starting pretty much covering the site. Right, so I'll click OK. That's fine, and we then define a figure of merit test. So this plots the bitrate to noise ratio over the area, right? And yeah, that's all we're saying here is we want to do axis constraint and plot the signal to noise ratio. Okay, and then let's plot it. So while it's loading, I'll kind of talk through what's going on. This allows us to verify the signal strength at different locations during our trajectory. We can use this to identify locations where it might be necessary to take additional steps to ensure proper communication. So here we can kind of see what's going on, right? So of course, the signal strength is strongest right around where we have our communication tower, and drops off the further we go. And we can see the minimum connection strength required for communication with this transceiver and a receiver setup was 50 dBm. At all ranges for our mission, the signal strength is lowest looks like 60. So indeed, we are able to maintain consistent and safe communication throughout the mission. Yeah, you're able to visualize that. So for more complex terrain or in a urban environment between buildings, this can be more useful and get very complicated as buildings block communication channels. But yeah, this kind of gives you an overview of what is possible and what we can do with SDK. Okay, moving on, we're gonna go to the ANSYS Electronics desktop, which is the ANSYS platform for simulating anything to do with electronics. This can go from anything like radios to radars to electric motors to printed circuit boards, you name it. All of these systems and much more can be simulated in this environment. So to show you an example of what we can do, I have a very simple patch antenna here. So you can see we drew up the model. We are going to define an excitation, right? So we're going to electronically excite this edge, right? So right over there of this antenna. It's just on a PCB, we have a layer shaped like this, and then a ground plane at the bottom. After exciting this antenna, we're going to study we're able to study its the electromagnetic fields emanating from this body, as well as its strength, how well it's able to radiate radiation, and yeah, it's kind of like its far field data to get a rough idea of which direction it's better at radiating than others, right? So we define the spectrums we want to analyze, and the first thing I want to go over is, here. So the terminal S parameter, the S parameter is typically used to identify the frequency for which the antenna is best suited. Here we can see that the antenna is best suited right around here, somewhere about, actually we can add a limit, add a marker. And right about here, we can see about 10.05 gigahertz. So that's the frequency that this antenna is going to work best at. It has it's able to best radiate its energy. Moving on, we can visualize the gain plot. So for the antenna that we showed, this is what the far field radiation looks like. You can see it's very directed, and of course, as you would expect, it's better at emitting radiation the direction that the face is facing. We can overlay this onto the model here. Let's see. Yeah, showing model window. So here we were able to visualize, okay, how exactly does that look on my antenna, right? So as expected, it's the strongest is in the direction that it's facing. The opposite direction has a weaker signal strength as well as some holes. Okay, we'll clean that out again so it's not cluttering our view. The other thing we can do is visualize the magnetic fields as they're emitted from this face. I'll kind of move us to a clean view, and we can do, there you go. Kind of stole my thunder. But so we're able to plot the magnetic fields on this face. We can also do is animate. So, dun-dun-dun. Okay. So we're able to see how the electromagnetic waves are carried through this antenna and their respective signal strengths as they're emitted. So this is a very useful tool to not only get the performance of antennas, but also visualize where its deficiencies and strengths are so we can use it to modify different designs. HFSS has also a lot of built-in tools to optimize the design of these antennas. Okay. Another example I want to go over is this. So electric motors, we've seen a lot of work on, and ANSYS also provides a simulator for these platforms. So there's a simple kind of dialog box version of this and also the extensive 3D model. We'll go over the simpler version first. Here you can define the number of poles, where the rotor is fixed, and then give it some losses to kind of define what the machine does. You define the diameters as well as the material that is used for the windings. And probably around here, you define what the rotor is as well. And if you define all these parameters that you know if you're designing the motor, you're able to analyze the motor and get an idea of its performance. Wait, wrong file. Here it is. So here's kind of a visualization of what that looks like, right? So here we have a motor. I've only done about, 1/8 of the motor. And you can see each of the windings are right around here, if I can click it. So this is only the top half. You could have a similar bottom half to the motor, and you can see those are the windings. You have the outer ring. If I can click it, we can kind of see it. The dark blue area here that includes the permanent magnets, and this is the inner motor where that's the one that's moving. So simulating the electromagnetics based on the materials that you define, the dimensions of everything, as well as just the electromagnetic coupling that allows you to have a motor. We're able to get the torques from the system as you simulate it from startup, the corresponding currents in each of the 3 poles, right? induced voltages, the flux, power flux, and magnetic field strength, and so on. We're able to compute all these information and predict the performance to simulate the electric motor, as well as output power and losses. So this is another application using the electronics desktop, where we're able to simulate electromechanical components to determine their performance before we even make it, and even optimize our design.
Hey guys, thanks Sammy for walking us through those demonstrations. That was amazing. So it's remarkable to see how far we've come from a simulation standpoint, and to see some of our real world assets in different situations, and the variables and the components that you can take a look at to pull new data sources and view the results of the simulation. It's remarkable for sure. We're now going to get into a little bit of Q&A. Excited to hear these guys answer some of these questions. First thing we're going to do is we're going to post the second poll question. So we're going to post that, and then if everyone can answer that, it'll be up for about 5 minutes or so. Again, we will send around the results of that poll in the post-event report. And now we're going to put you guys on the hot seat and get into some questions. So the first one we're going to ask is from Eamon. So he has asked, how easy is it to integrate the vehicle model and add new sensors to the simulation?
It's actually very simple. So right now we actually have our Lexus model in there. So we could actually model any car. So far, give us a nice 3D model. And to add the new sensors, we have our sensor labs. Sammy explained in his demonstration that it was pretty straightforward, and we could locate the sensors needed such that we could actually run our AVX simulation. Sammy, can you elaborate?
Yeah, so as Barry was saying, the sensors we cover, they're optical cameras, LiDARs, and radars. And regarding the vehicle model, I'm guessing you're talking about the dynamics. Yeah, you can simulate, whether it's all-wheel drive, front or forward-wheel drive, rear-wheel drive, whatever the tire models you want to use. And we've used CarMaker, Carla, as well as Weebots. There's a lot of flexibility to really incorporate, even MATLAB if you want. The world is yours.
Great. Thanks, guys. Next, we have Marcus. So he's wondering which ANSYS tools we would best recommend for computational fluid dynamics.
Okay, so it's depending on your application. If we talk about electronics cooling and battery cooling, so anything to do with integrated electronics, so it will be ANSYS IcePack, which we have here. Now, if you want to talk about drone simulation, drone flights, that will be ANSYS Fluent. Those are the answers.
Got it. Thanks, Barry. Jennifer's wondering, how accurate is simulation in comparison to real-world testing?
It is fairly accurate, actually. So what we actually did a test on, we take an experimental data from our Lexus vehicle, downloaded the data, and we plot the path of the vehicle with its GPS and compared our optical cameras in real life with the simulator, and they're almost one-to-one match. So I'm confident that simulation is very accurate enough that in a lot of cases you can replace your real-world data with simulated data.
Got it. Thank you. Evan's got a bit of a two-parter here. So does SDK identify if mission parameters conflict with drone performance? And then as an example, if the area to be scanned is larger than the battery range of the drone model selected, will it generate a path back to be recharged before continuing the flight path?
Short answer is no, because SDK does not have that ability yet. I don't know yet. So we have to go consult with the ANSYS application engineers. But what we can do is some engineers, Sammy and I, we could actually do the simulation, and if we see that it will run out of battery, then we'll actually modify the scenario such that we'll have a two-part. So we'll fly, let's say, half the path, comes back, recharge, and then we'll fly again for the other half of the path. So again, like, even though SDK can't do it, SDK can't do it at this point. We can do it with our modified software.
Got it. Another question here. can the simulation be applied to other industries besides smart mobility?
Absolutely. It applies to everywhere. It applies to the aerospace industry, space industry, energy, defense, you name it, anything that deals with engineering or science, simulation could actually be applied.
Got it. Hay has a question here. Can the platform access ANSYS CFD as well?
Okay, so for those who don't know, CFD means computational fluid dynamics. At this point, it's only IcePack for now. ANSYS IcePack.
Got it. Here's the next one. Can you identify any limitations of simulation? Thank you for your presentation.
Thank you. So the limitation of simulation in the short run is basically what do you put in parameters. So sometimes simulation can't simulate every single aspect, every single part of the of a structure. You might miss one. Let's say you might miss a crack in the aircraft, and you're doing structural analysis. You think the aircraft's fine, but you miss a crack, then it will fail. So it's the biggest limitation will be computational power. That is the biggest limitation. So if you have a simulation that has really fine meshes and you're doing fine element analysis, if you're expecting to have like a 10-minute turnaround time, you'll be wrong. It could be 10 hours or 10 days or 10 weeks.
Got it.
Yeah. Kind of add a little bit on that to address that need. What we're providing with our simulation services is access to our computers. We have the workstations necessary that have the computational power, the memory that's able to simulate these problems very fast. So it's not necessary for the clients to have a supercomputer in order to run the simulations. We can take that 10 days of runtime simulation time down to 10 hours, using our computers. So that's another free service we're providing.
Perfect.
Exactly.
Maybe one last question then for each of you. So Barry, what excites you most about the future of simulation?
What excites me the most about future simulation is that we will actually have more computational power. We can actually do more different physics-based simulations, such that we don't have to build so much expensive prototypes, and people can actually imagine the wildest designs without any limitation, just having the wildest dreams imaginable.
Nice. And Sammy, for you, what excites you about working with simulation each day?
Yeah, so one thing that I really do believe in is knowledge is power. What simulation lets us do is it lets us know what's going to happen and not suffer the consequences, actually having to make the product, run the simulation, and then find out, oops, we have a problem. Simulation allows you to circumvent that and identify these issues before, where it's easier to actually solve them. That's what
Perfect. All right, thanks very much, guys. So in conclusion, I want to thank everybody for attending today's webinar and for getting the dialogue started with our community for sure. We want to invite you to become part of the community and to visit our website or use our QR code to register for the free simulation portal. It has unique free content, information about future webinars, and more. And if you have any questions about simulation or the opportunity to engage with us, please contact us at simulation@areaxo.com. We'd love to hear from you and to offer you as much information and advice and support as we possibly can. So thanks for your attendance today. Have a great day, everybody.